Here's an example for an ordinary differential equation. It's going to be for a velocity of a falling object, and it's going to try and illustrate what the initial conditions actually mean and why they're necessary. All right, so for this problem, we have v of t, v for velocity. This is how I draw my t's. They don't look like pluses. It's cursive. Is the velocity at time t. We've got m is the mass, which is going to be 4 kilograms in this example. We've got k, which is the drag coefficient, which is going to be 0.5 kilograms per second. The reason it has such weird units of measure is because it has to agree throughout the entire equation. We're going to use g is the acceleration from Earth's gravity, which we're just going to say is 9.8 meters per second squared. And we're also going to say that at time 0, when we start this experiment, the velocity is 10 meters per second. Right, so it's going up a little bit. It's going away from the Earth. All right, so now to make the differential equation, we have some object, right, something, and we know that it's going up at 10 meters per second. We know there's a pull of gravity from the Earth, so let me just draw Earth. That's pulling it down, and that's going to be the g component. And then we also have, in this case, drag is always the opposite of the direction. So if it's traveling up, the drag is going to be down. So let's try and make a differential equation for that. So the first thing we have is force equals mass times acceleration, right? But acceleration in this problem is going to be, well, m is m, that's the mass, and v is velocity, so v prime is the acceleration. And then that has to balance with all the other things. So we have gravity, which is going to be negative mg, right? So there's a certain amount of pull from gravity, and it's proportional to the mass of this object. We also have minus k times v. Right, so the drag here is proportional to the velocity. So right, if it's going faster, the drag is going to be bigger. And so if it's going, 10 meters per second, it's going to be 10k. If it's going 20 meters per second, it's going to be 20k, something like that. And then another thing to keep in mind is this minus. So right, if the object had been going down instead of up, so let's say, that's negative 10 meters per second, the drag would have gone upwards, right? And then we would want the drag to actually point up. So in order to get this to point up, we'd want a negative velocity times this positive k. It would end up being a velocity going upward, right? So positive velocity is going up. All right, so hopefully that was a somewhat decent explanation, but now let's go ahead and plug in numbers. We're going to do one thing first, though. So we're going to write v prime here, and for units, let's figure this out. So let's look at that as well. So if I write this out, it's m dv dt equals negative mg minus kv. The reason we have the units we have is this ends up being kilograms. And kilograms. And then dv dt is meters per second squared equals the negative mass. So in this one we have kilograms. And then the g is meters per second squared. And the v here, if I have the k, the v is meters per second. Excuse me. And so if I have kilogram meters per second squared here, if I have kilogram meters per second squared here, I need to have kilogram meters per second squared here. I'm missing a kilogram on top, a meter on the bottom. So that's why the k actually has units of kilograms per second from up here. All right, so now let's go ahead and plug these in. So I'm actually going to simplify this a little bit if I can. I have the m everywhere. I want to get the dv dt by itself, so I'm going to have dv dt equals, I'm going to divide everywhere by m, so I end up with a negative g minus k over mv. Then if I actually plug things in, so I have dv, all right, dt equals negative 9.8 minus 0.125. So I took the half and then I divided by 4, so it ends up being 0.125 v. So we don't know how to solve this yet, but the solution to this particular ordinary differential equation ends up being v of t is equal to a constant times e to the negative 0.125 t minus 78.4. To kind of make sense of this, the constant here is allowing you to solve for any initial velocity, right? So in this particular case, I have 10 meters per second as the initial velocity at time t equals t sub 0. But what if it had been 20 or 15 or negative 4? It could have been any initial velocity. So the reason that the constant kind of exists and why it needs an initial condition is the initial condition specifies what that constant is supposed to be. This thing controls the initial velocity that we're going to actually have when you plug this in. Right? We don't know what c is yet. To solve for c, you pretty much do this. You say v at time 0, well, that equals c times e to the negative 0.125 times the number 0 minus 78.4. Well, this thing is 0, e to the 0 is 1, so that's just c minus 78.4. But we also know another thing. We know that v at time 0 was 10. We specified that over here. The initial velocity is 10 meters per second, which means it's going upward away from the Earth. So in order for that to work, c has to equal 88.4. And so now we can actually write for this initial value problem, we solved the ODE in general, and then we picked, and with the initial condition, we were able to pick the constant of integration to get a particular velocity at time t equals 0 that was specified in the problem statement. And so the solution for our initial value problem is v of t equals 88.4 e to the negative 0.125, let me complete that 0, t minus 78.4. All right, so hopefully that gave you a little bit of intuition on what the initial condition does in terms of physics. It's kind of where the system started at, and the system being whatever physical system you're describing. So in this case, the physical system was an object that was in Earth's atmosphere, and it had gravity acting on it as well as drag from it flowing through the atmosphere. And so you've solved that in general, and you get this constant integration that shows up, which you'll figure out later on. And then from there, you have to pick that constant integration so it solves your initial condition that you're given, so that you can predict now, if this object was going 10 meters per second upward, I know what it's going to be doing in 1 second and 2 seconds and 3 seconds. Eventually it'll turn around and it'll start falling, and you'll be able to predict the velocity at any time. But in order to predict the velocity at any time, right, you had to know what it was doing when you started your experiment. And then your solution has to match what it was doing when you started your experiment. So that's what this C does. And so that's the first order differential equation, and hopefully in the next one you'll get an even better understanding of these constants of integration and the initial conditions and why we need them.